Hello, Cal 2 students, and welcome to another lecture in Calculus 2. Last time, our lecture covered the derivatives of inverse trig functions. So the natural thing to do now is to reverse engineer all of those differentiation formulas that we got for inverse trig functions so that we can get integral formulas that yield inverse trig functions. And let's see how we might go about that. If the derivative of inverse sine of u is this mess, then it stands to reason that if we compute the antiderivative of this, we should get the thing that we started with, plus some constant. And this is exactly how it turns out. And similarly with arctangent, it stands to reason that if we integrate this thing, we get the original function plus a constant. And that turns out to be true. And with the arc secant, because of the absolute value bars, we're going to make a slight alteration, but just very slight. In our formula, or in our integrand, we won't have absolute value of u. We'll just have u. And what this turns out to be is the arc secant of the absolute value of u plus c. And everything that we've done here is correct. The antiderivative or integral of this thing is the arc sine of u. The integral of this thing is the arctangent of u. And the integral of this thing is the arc secant of the absolute value of u. And you know what? We're not going to use any of these formulas for our integration. These three formulas will not be among the formulas that we have to memorize. And here's the reason why. This formula is correct, but hopefully we can do better than this. Hopefully we can get a formula similar to this one that is more general than this formula. Well, what would such a formula look like? Instead of computing the antiderivative of 1 minus u squared under the radical, let's just generalize things, because we may have something that looks kind of like this that we want to integrate, but maybe this thing right here isn't 1. Maybe it's some other positive number. So this formula, we're going to generalize it so that the first term under the radical isn't necessarily 1. It's just some positive number. And we'll stipulate that a is greater than 0. Well, if we can do that, if we can generalize this formula in that way, we ought to be able to do the same thing for this one, right? And the fact of the matter is we can. And also the formula that gives us arc secant. We're going to generalize these formulas to look like this so that they will allow us to integrate a larger class of functions. Now, don't worry about writing these down yet. I'm going to work through at least one of these to show how we generalize it. And then I'll write down the generalizations for all three. In finding the antiderivative of this expression, we're not going to ignore the result that we had previously. We're not going to ignore it. We know that the antiderivative of 1 over the square root of 1 minus u squared du, we know that this thing is equal to arc sine of u plus c. We know this, and for the next 10 minutes or so, we're not going to forget that we know this. We are going to use this formula to get a more general formula here. So, let's have at it. Somehow, I'm going to try to get this formula to look like the one that we already know. Forgive me. I had forgotten how it is that I go about doing this. So let me do it this way, because I realized that if I start off with u's, I'm going to have to use U-Substitution. But I'm already using u for something else. So let me write the integral this way. We'll get the integral for this, the integral formula for this, and then just generalize it for when we have a squared minus u squared du. Here's what I'm going to do first. I'm going to factor a squared out of both terms. Let me see, does this work? A squared times 1 is a squared. A squared times x squared over a squared is x squared. Okay. Marvelous. I haven't changed anything. This is the exact equivalent of what we started with. And now I'm going to use the property that the square root of a product is the product of the square roots, provided that both of the factors are non-negative. So what that means is I can write this as the square root of the first factor times the square root of the second factor and remember, I didn't write it down here, but earlier we agreed that A was going to be positive. And what that means is that when I compute the square root of A squared, I don't have to worry about absolute values or anything like that. If A is positive, the square root of A squared is just A. And this mess, I'll rewrite it slightly. If we have something squared divided by something else squared, we can rewrite that as a quotient, the whole thing squared. So nothing magical or mysterious yet. This 1 over A, this constant here, normally I'd move it out in front of the integral sign. But here, because I sort of know where I'm going to take this A and I'm going to move it out in front of the differential dx. Oops. Okay, so far so good. Now here's where I use U-substitution. You see, I don't have 1 minus x squared here. I have 1 minus some function of x squared here. So I'm going to let u equal x over a, and that means that du dx is going to be 1 over a, and that du is going to be 1 over a dx. And I am going to analyze this in terms of u. And you know what? I didn't leave myself much wiggle room here. Let me just push this over a little bit. I'm not rewriting anything. I'm just moving the expression further to the right. Okay. I just moved it farther to the right because I want to analyze this in terms of u and du. And here's what I have. X over a is u. So x over a squared is u squared. And this 1 over a dx, that's du. Son of a gun, this fits a form that we already know. 1 over the integral of 1 over the square root of u squared. Let me try it a third time. 1 over the square root of 1 minus u squared du. This fits a known form. This was going to be the form that we were going to memorize. We know what it is, but after we compute this derivation, we're not going to care about this formula anymore. Here's what we get. We get the inverse sine of u plus c. Well, what is u? U is x over a. Now let's just recap our result. We started here, and we ended up here. And don't draw this red stuff on in your notes. Don't circle this and don't circle that and draw the line, because I'm going to restate this result after I erase the board and there's less clutter. Here's what we just established. We came up with an integral formula. The integral of 1 over square root of a squared minus x squared dx is arcsine of x over a plus c. Is this the formula that we want? Not quite. We will alter this slightly to get the formula that we do want. Okay, this is the formula that we're after. This is the, whoops, it would be the formula that we were after if I wrote it correctly. Okay, there we go. This is the formula that we're after. This is the one that we're going to memorize because it generalizes everything perfectly. What happens if this isn't x squared? Maybe it's a function of x squared. Okay, so we have u instead of x, and this is what we get. Oh, what happens if this isn't a 1? It's some other positive number. This is what we get. Now, we did remember that we agreed that a was greater than 0. No big deal. So this is the first of the integral formulas that we're generalizing. Let me write the others down now. Here are the integral formulas that give us inverse trig functions when we integrate. I think there are a few things that I need to stress. U in these formulas is always the function of x. And A is always the constant. So if we have constant minus function under an integral, this is the formula that we use. Now, if we have let's see. If we have function minus constant under the integral sign, this is not an arc sign problem. This is not going to give us arc sign of anything. If we have function minus constant under the radical sign, do not say, here's my a squared and here's my u squared. No, don't do that. It won't work. Don't use the integral of 1 over square root of a squared minus u squared du. It won't work. This formula was derived under the assumption that a was a positive constant and that u was a function of x. So when we use this formula, the positive term under the radical has to be the constant. The term with the negative sign in front of it under the radical has to be the function of x. So if we see something like this, function minus constant, we might try to use this expression because we do have function of x minus a constant. So if we have in the denominator function minus constant, we might try to use this formula. The only thing that's bothering us here is that we don't have u out front, do we? Now, algebraically, we might be able to alter this expression so that we can get u out front here and so that we can get du here. If we have u, square root of u squared minus a squared in the denominator, full speed ahead, this is an arc secant problem. If we have u squared minus a squared, let's say dx here, we might be able to work things out algebraically to make it fit this form. we might be able to work something out so that it fits this form. If we have something like this and we can use one of these three formulas, the formula that we're going to have to use is the one that gives us arc secant. Because under the radical, we have function minus constant. If we use one of these three formulas, it's going to have to be the one that gives us arc secant. We can't look at this and say, oh, you know what? There's no u out in front here, so we got to use this formula. If we have something like this, we cannot use this formula. Under the radical, very specifically, we have constant squared minus function of x squared, and that is not the same thing algebraically as function squared minus constant squared under the radical. So if we have something like this, we don't ever use this formula. Now, suppose we have something that looks like this. Let's see. Suppose we have something like this, and we say to ourselves, oh, wow, you know what? If we rewrite it, this is 3 squared minus x squared squared dx. We've got u here, we've got u squared there. Oh, but wait a minute. Wait a minute. We've got something out front here, and we've got the difference of two things under the radical, two things squared. We can use this formula. No, we can't. Oh, but we have u out front here, and we've got the difference of two things under the radical. That's true. But let's analyze what it is that we do have under the radical. We have constant minus function of x under the radical. And the formula that gives us arc secant has under the radical function of x minus constant. The two things are completely different, and we can never, ever, ever use this formula to compute the antiderivative of something like this that has constant minus function under the radical. And again, I'm going to say don't use this formula to compute the antiderivative of something like this. It's tempting because on the bottom we have something times a radical that has the difference of two things. And in our formula we have something times a radical that contains the difference of two things. But they don't match up. Under the radical we have function minus a constant here in the formula. And down here under the radical, we have constant minus a function under the radical. In plain vernacular, it ain't gonna work. We can't do that. Suppose we have something like this. 1 over some function of x squared plus some constant squared. Can we use this formula? Should we try to use this formula? And the answer is yes. And you might say, well, we couldn't do that for this one, and we couldn't do that for that one. Why can we all of a sudden now turn things around and say that this is the integral of 1 over a squared plus u squared du? What gives us the right to do that? And the answer is this. Unlike subtraction, which we have up here and which we have down here, unlike subtraction, addition is commutative. We can switch the order of the terms. And so this is exactly the same as that, which does in fact fit this form, constant squared minus function of x squared. So if we have the sum of two things in the denominator, we can call the function u squared, we can call the constant a squared, even if the function comes first and the constant comes last, because addition is commutative. X to the fourth plus 9, exactly the same thing as 9 plus x to the fourth. And that does fit this form, 1 over constant squared plus function of x squared. So with something like this, it doesn't matter which term comes first. We can always rewrite it to put the constant first and the function of x second. Now, there's one more thing that I have to address, and it doesn't really have anything to do with the misuse of these formulas. It has something to do with the fact that we only have 3 integral formulas that yield inverse trig functions. We had to memorize the derivatives of all 6 inverse trig functions. So why shouldn't we have 6 integral formulas that yield inverse trig functions? And I'll answer that next. Some of you have probably been wondering about this. Why don't we have integral formulas that yield arc cosine, arc cotangent, and arc cosecant? Yes. Why don't we have integral formulas that yield arc cosine, arc cotangent, arc cosecant? And here's why. The derivative of arc sine, and we'll just say x, is equal to 1 over square root of 1 minus x squared and the derivative of arc cosine of x is negative the integral of 1 over 1 minus x squared as a consequence, when we integrate 1 over 1 minus x squared dx, we get arc sine of x, right? Plus some constant. That's what we get. If we integrate this thing, we get exactly what we started with. And so far, it looks like I'm undermining my argument for why we don't have formulas that yield inverse cosine and inverse cotangent and so forth. Whoops. Maybe I should put that over here. I'm going to start out with the same integral down here that I have up here. And let me ask you something. What do we usually do with an integral when we have a constant inside the integral sign? Don't we usually take that constant factor and move it out front? You bet we do. And we do the same thing with this factor of -1 here. Just move it out in front of the integral sign. And now this integral is computed using this formula. And we get arc sine of x plus c with that negative sign out front. And so we realize if we did have an integral formula that would yield inverse cosine, the thing that we might naturally do is take this negative sign and move it out front. And that will give us the opportunity to use an integration formula that we already know, the integration formula that gives us arc sine of x. And we just take this negative sign and move it out front. So could we use this formula to integrate that integral? Yeah. But usually when we're given an integral and there's a constant in front of and there's a constant factor of the integrand, like -1, we'll take this constant factor or this negative sign and we'll just move it out in front of the integral and then compute the integral. And consequently, we get something involving inverse sine. The only difference between the integral formula that gives us arc sine and one that would give us arc cosine is just a negative sign as part of the integrand. So instead of having a separate formula for arc cosine, we just take the formula for arc sine and we get this negative sign out front. If we got a negative sign here as part of the integrand, we just move it out front and we get negative arc sine. The same kind of thing happens with formulas that would give us inverse cotangent and inverse cosecant. The only difference between the formulas for inverse cotangent and inverse cosecant is that there would be a negative sign or a factor of -1 as part of the integrand. And we could have a separate formula for arc cotangent and arc secant. But instead, we just take that factor of -1 that's part of the integrand and we move it out in front of the integral sign and just get the corresponding integral formula for arc sine, arc tangent, or arc secant. So that's the long and short of it. We don't need formulas that give us arc cosine and arc cotangent and arc cosecant, because we can use the formulas that we have that give us arc sine, arc tangent, and arc secant. And we mathematicians are not completely unfeeling people. See, as far as integral formulas that yield inverse tangents, we're only giving you 3 to memorize instead of 6. And you probably appreciate that, because I know you're already buried under a myriad of formulas. Having to memorize 3 instead of 6 additional formulas is a blessing. So this is why we only have integral formulas that give us this is why we have integral formulas that only give us arc sine, arc tangent, arc secant. The other integral formulas can easily be rewritten so that instead of giving us arc cosine, arc cotangent, arc cosecant, we get arc sine, arc tangent, arc secant. So in the name of simplicity and the fact that we don't need to have any more integral formulas, we only have formulas that give us arc sine, arc tangent, arc secant. Now, enough of this lecturing. Let's do some examples. Let's do a lot of examples. Here's a nice one. And maybe, hopefully, we can use one of our formulas to do this. Now, which one are we going to use? Notice what we have here. Under the radical, we have constant minus function. So it makes sense that we're going to use or try to get what we have to fit this form. And let's see if we can. A squared is going to be 9. A is going to be 3. And let's see, u squared is going to be 4x to the 4th. U is going to be 2x squared. Du dx is going to be 4x. Du will be 4x dx. And let's see how this matches up. This is u squared, which means that u is 2x squared. And this thing is a squared, which means that a is 3. So far, so good. It appears that I'm looking at 1 over square root of a squared minus u squared x dx. I don't have x dx here, but if I multiply both sides by 1/4, or if I divide both sides by 4, I get x dx. So it looks like we have 1/4 du here. Okay. We're only off by a constant. We're only off by a constant, 4 or 1/4. So I think this is going to work. And let me ask you something. What do you think I'm going to do with this factor of 1/4 here? Move it out in front of the integral sign? You'd better believe it. That is exactly what I'm going to do. This is a formula that we know. I'm going to have 1/4 and times the integral of this thing, and that integral is arc sine u over a plus c, which equals 1/4 arc sine. And what's u? 2x squared. And what is a? 3. Ah, wonderful, wonderful, wonderful. Okay. And I summarize things here. Oops. This was a good one to start off with. Not completely obvious, but not terribly complicated either. And bit by bit, we'll venture into more hazardous terrain, but we'll do it bit by bit. The next exercise, we're just going to throw in one extra curve, if you might call it that. One little snag that we can overcome easily. Here's a good one. It involves us getting slightly out of our comfort zone, or maybe expanding our view of something just a little bit. Does this give us an inverse trig function when we integrate? Let's see. I might try to do this without using inverse trig functions, especially if I don't see right off the bat that, this fits one of our inverse trig formulas. Let me rewrite it slightly. can I do this? Can I say that this is 1 over u, and this is some constant times du? Can I do that? Maybe I can. Let's just chase this down and see where it leads. U equals 5 plus sine of x squared. So du dx is going to be, derivative of 5 is 0. Here we have a function raised to a power. So we're going to get the power rule as usual, times the derivative of the inner function. And let me just simplify that a little bit. I'm going to get 2 cosine of x sine of x. And du is going to be 2 cosine of x sine of x dx. Okay. Here's our 1 over u. But now I see a very big oops coming. What's left over doesn't have to be exactly du, but we can't be off by more than a constant multiple. Here's du. We have cosine dx. Maybe I could look at it this way. This is equal to 2 sine of x times du. What we have left over is not a constant multiple of du. As long as we're only off by a constant multiple, that's good. Because in the integration process, we'll just take that constant and we will move it out in front of the integral sign. But this is not just a constant multiple times du. 1 over u du, it ain't gonna work. Okay, we went with, well, maybe it wasn't our first hunch, maybe it was our second hunch. And because we weren't completely sure about the first hunch, we chased down our second hunch first and it didn't pan out. So now maybe we're going to go back to what was our first hunch all along. Here's what I'm thinking. I'm thinking that it actually does fit the form that gives an inverse trig function. And since there's no radical here, it's got to be the formula that gives us arctangent of something. So I'm going to rewrite this. And I want to make it fit the form integral of 1 over a squared plus u squared du. I want to make it fit this form. And we panic because we say, wait a minute, that's not a perfect square. This isn't 4, it's not 9, it's not 16, it's not 25. This isn't going to work. Well, wait a minute. In our formula, all we stipulated is that A is a positive constant. We never said that A had to be a perfect square. This is going to be my A squared. This is going to be my U squared. And this thing, some constant times du. But how is that going to be A squared? Well, let's just write things down. Like I said, we're going to get a little bit out of our comfort zone, or maybe we're going to expand our view of things just a little bit. Let's write down what we have. A squared is 5. Whoops. So what is 5? What is A? Square root of 5, right? Hey, it's a positive real number, no problem here. U squared is sine of x. So U squared is sine squared of x. So U is sine of x. And du dx is cosine of x. Ooh, this is working out nice. And that means that du is cosine of x dx. This is a squared, that's u squared. And cosine of x dx is our du. So we're not even off by a constant multiple. We just got du here. Oh, this is going to be great. Look at this. 1 over a squared plus u squared du. This is the standard formula that gives us arctangent of u. And what is that formula? Isn't it 1 over a arctangent u over a plus c, where a is square root of 5, and u is sine of x, and you know what? If we need to rationalize the denominator to make it match the answer in the back of the book, we can. It's never hurt my feelings when somebody leaves a radical in the denominator. So if you leave it like this on a test, I'm going to be happy as a clam at high tide. So let's just summarize our results. There's our result. And before we go on, let's just make sure that we got the point of this exercise. When we see one of these formulas for arc trig functions, and we have a squared does not have to be the square of an integer. A squared can be any real number. And that means that a doesn't have to be a natural number or a whole number. A can be an irrational number like square root of 5. A squared doesn't have to be the square of a whole number. And a doesn't have to be a whole number. A squared just has to be some positive number. That's all. This didn't even have to be a whole number. So a squared doesn't have to be the square of an integer or a whole number. It just has to be a positive number. And we can still use this formula and the other formulas that give us integrals yielding inverse trig functions. Now, let's get a little bit nastier in our examples. Here's a good one to look at. Now, let me just play devil's advocate and say that we don't try to match it up with one of the formulas that yield an inverse trig function. Maybe we want to do just straight U-substitution. And so I could look at this as 25e to the 2x minus 4 to the 1/2 dx. And this would be my u to the 1/2. And that would mean that u would be 25e to the 2x minus 4. And du dx is 50 e to the 2x. And du is 50 e to the 2x dx. Son of a gun. We don't have to have exactly du here. We have u to the 1/2. This doesn't have to be exactly du, but it at least has to be a constant multiple of du, and we ain't got it. There's no constant that we can multiply dx by to give us this mess. We don't have to consider the direct U-substitution approach any further. It ain't gonna work. So let's go and do it the way that we kind of figured that we needed to do it all along. Let's take a look at what we got. We have a radical, and under the radical we have the difference of two things. And we have function minus constant. So of all of the formulas that yield an inverse trig function when we integrate, there's only one that it can possibly fit. And that's this son of a gun. Under the radical, we have function minus constant. This is the only formula that we know where the radical in the denominator has function minus constant. But do you see the problem? Well, actually, there are two problems here. We may not see both of them, but I'm sure we see at least one. Whatever u is, or whatever u squared is, we're supposed to have u out in front of the integral, and we ain't got it. This looks like it ain't gonna work. We're not even gonna get out of the starting gate. But let's just see if maybe we can take what we have and through hookery and crookery, somehow we can get this thing to fit that form. Maybe we can't do it. When we tried the straight U-substitution approach, that didn't work. And we kind of knew that it wasn't going to work, but we tried it anyway. Doesn't look like this is going to work, but let's make sure that it doesn't work, okay? This has got to be u squared, and that has got to be a squared. Okay. And we look at this thing, and we're not even sure if we can write this as something squared. But let me just show you something that you might not have thought about before. How can we rewrite this in simpler form? Look what we have. We have something raised to a power, and that whole thing raised to a power. When we have something raised to a power and that whole thing raised to a power, what did the exponents do, huh? Right, they multiply. This is an eye-opener. E to the 2x is the same thing as e to the x quantity squared. Now I know how to rewrite that. And this is an integer squared. No trouble rewriting that as a perfect square. Let's start writing things down. A squared equals 4. A equals 2. U squared equals 25e to the 2x, which is the same thing. Remember, e to the 2x is e to the x quantity squared. So this is going to be 5e to the x quantity squared. Let's see, does that work? We square the 5 and get 25. We square e to the x, we get 2x. Yep, that works. And that means that u is going to be 5 e to the x. Well, it's looking better already. It really is. Now, I still don't know what I'm going to do about the fact that we don't have a u out front. But like I said, by hook or by crook, or by hookery and crookery, maybe we can manipulate this algebraically so that it will fit exactly the formula that gives us inverse secant. Let me rewrite what I have so far. And that was 5 e to the x quantity squared minus 2 squared Now, let's see where we're coming up short. We need a u out front of the radical, and we don't have it. That's very problematic. And that may be enough to keep us from doing this integral successfully. But let's work with it for a minute. Here is our u. I'm going to leave a space I'm going to leave a line right here. I have an ulterior motive. Du dx is going to be 5 e to the x. Okay. Du is 5 e to the x dx. And 1/5 du is e to the x dx. For my du, I don't need 5x dx. I'm sorry. For my du, I don't need 5 e to the x dx, although if I had 5 e to the x dx, that would be nice. But if I only had e to the x dx, I'd have a constant multiple of du. So instead of having du, I'd only be off by a constant multiple. That would be okay. Ew. At the very least, I need an e to the x in front of this dx. So there's another problem. One problem is that I don't have u in front of this radical. And what is u? It's e to the x. And you know, I don't really need 5 e to the x here for my u. If I just had e to the x, I'd be okay. But let's see what I'm missing. What am I missing? In order to make this thing du, this should be 5 e to the x dx. And this is all I got. So that's problem number one. I'm missing 5x, I'm sorry, I'm missing 5 e to the x here. Now the 5 is not that important, but the e to the x, that's a problem. I don't have it here. To get du, I would like to have 5x. To get du here, I'd like to have 5 e to the x here. And I ain't got it. And that's not my only problem. I need a u out front here. And I ain't got it. Now, I don't need u here. I could, if I were off by a constant multiple, that would be okay. What is u? Oh, u is 5 e to the x. I'm missing u here, where u is 5 e to the x. And to make this thing du, I'm missing 5 e to the x here. I have two problems. But if I fix one, maybe I'll fix the other too. I need 5 e to the x here, and I ain't got it. I need 5 e to the x here, and I ain't got it. Let me just write down what I want. Hey, I can't just do that. I can't just stick a 5 e to the x in here. I can't multiply something by 5 e to the x. You're right, I haven't. I've sinned. I've multiplied something by 5 e to the x. I've changed the value of that thing. Now I've got to make atonement for my sin. And I can do that if, after multiplying by 5 e to the x, I divide by 5 e to the x. And you know what? I'm going to do it right here. Oh my goodness. This is u here. Exactly what I needed. This whole thing is du. Exactly what I needed. And let's make sure we understand this. I haven't changed the value of the expression at all. I multiplied the numerator by 5 e to the x. I multiplied the denominator by 5 e to the x. So in other words, I multiplied by 5 e to the x, I divided by 5 e to the x, I multiplied the whole thing by 1. I haven't changed the value at all. But through algebraic trickery, I now have 1 over u times square root of u squared minus a squared du. This is exactly what I have. Son of a gun. Oh, this didn't look like it was going to work out at all first. My formula gives me 1 over a arc secant u over a. Whoops, that's not quite right, is it? Got to fix that. 1 over a arc secant of absolute value of u over a plus c. A is 2, u is 5 e to the x. And you know what? I ain't going to put absolute value here. Not because I'm stubborn, but our u is 5 e to the x. Think about what the graph of e to the x looks like. Here's the graph of e to the x. It's asymptotic with the x-axis, but it never actually touches the x-axis, which means, whoops, y equals e to the x, which means e to the x can never be 0. It can never be negative. The graph of e to the x lies above the x-axis. E to the x is always positive. So I don't need these absolute value bars at all. Now let me just summarize our result. Ah, this is beautiful. Oh, things started out looking so badly, but we pursued it, we chased things down, we did a little bit of algebraic manipulation, a little bit of, well, what do I need here to make this right? And a little bit of, what do I need here to make this right? And it all worked out. This is a nice example for us to work again, because sometimes when we have more than one thing missing, if we fill in what we're missing, everything takes care of itself. We were missing u here. We were missing du here. When we went ahead and filled in one of those things and then compensated, we ended up supplying the other thing that we were missing as well. So remember this exercise. This is a really good exercise to do over once or twice.